All right, so let's talk about the normal distribution today. A few announcements. So as usual, we have our vitamin due on Friday. Because some people had power outages this week, we've made the homework 8 due on Friday now. So it's one day later, and then you can turn it on Thursday for the bonus point. Similarly, project 2 as well, the first checkpoint, we've pushed that out, the due date to Saturday. So you have one extra day there. Um, and then next week, because we have the election going on, we decided to just make all discussion sections optional. We want to make sure you guys are able to go out and vote. And Tuesday sections in particular are also canceled. So if you do have a Tuesday section normally, you'll get an email with alternate times that you can go to. So there'll be kind of several times to choose from. You won't just have to go to one. But yeah, so if you can vote, if you have the privilege to vote, please do so. And we're just do whatever we can to make it easy for you to do that. So yeah, that's the main announcements there. And then kind of just continuing on with what we talked about last week, or on Monday rather, we started describing like the center and spread. So how can you actually describe distributions using just a couple numbers? And then why is that useful in terms of being able to estimate beforehand or guess beforehand where most of the values in your distribution lie? So we talked about how Chebyshev's inequality allows us to do that. And so there's actually like a formula there. And so today we'll kind of continuing that discussion, finishing up some stuff around standard units, which we didn't totally get to completely, and then going into bell-shaped curves, which are a very interesting type of curve and that have really useful properties for all kinds of sampling. So just to kind of quickly recap what we talked about with standard units. So, we went over the definition of standard deviation, and then we said that sometimes it's really useful to be able to understand your data in relation to the standard deviation. And so if you have your data in some units, like if you have age in years, for example, within a sample, it might be really useful to understand what's the age of this individual in standard units, meaning like how many standard deviations are they above the average? So are they like positive standard deviations above? Are they negative standard deviations? So where are they relative to the average? And the reason this is important is because it allows you to compare different distributions. So if you have like the same individuals and maybe you're measuring two different variables about them, and you want to compare what those variables means, if you want to have some context of comparing those two distributions together when they might be in different units or have completely different just understandings, then putting them in standard units allows you to do that. That's why we do that. And that's why they're called standards. You can put every distribution into standard units. And the way you do this is you take whatever value you have of the individual in your sample and then subtract the average value of all the individuals. So basically that tells you the deviation. So that's how far that individual is above the average. And then you divide by the standard deviation, which is how far people are from the mean on average. So the reason you divide by standard deviation is to just scale things down, because some distributions are really wide, some distributions are really narrow where everything's all clumped together. But when you divide by standard deviation, it accounts for that. And so then everything gets on the same kind of scale, essentially. That's why we do that. And so when you do this calculation, if you have a value that gets converted into something that has a negative z, that means that the value is below the average. If it gets converted to something that has positive z, it means it has a value above the average. And then if it has a value where z equals 0, that means it's equal to the average. And so one interesting property is that when you convert a distribution of values into standard units, then the average of the standard units is going to be 0 always, and then this SD is going to be 1. So we talked about that last time. And so I want to show you just one example because I think it's really useful. And someone actually brought this up in the last lecture, which was looking at test scores and comparing like your midterm to your final, and getting a sense of like did you do better on one or the other. And so let's actually look at an example of that. So this is an example of scores from fall 2018 data 8. So we'll read this in. So these are some scores here. So like each row is an individual, and then we have their midterm score, their final score. And so, you see like this first person got 91 and they got 88. This person got like 87 and then 88. So what's interesting is, if we focus on this person, this fourth person, they got an 87 on the midterm, but they got an 88 on the final. So in terms of a raw score, it looks like they did better on the final. But things are relative too in terms of where the distribution is. if the distribution of the midterm is like a lot higher than the distribution of the scores on the final, then an 87 actually might be better, might be worse. So it just depends on the distribution where the center is and what the standard deviation is. So let's actually take a look at these distributions next to each other. So I'll zoom out a little bit here. So on the top, we have the midterm scores, and then the bottom of the final scores. So in this particular example, it looks like there's more variability in the final scores. It seems like they're a little bit more spread out, whereas the midterm scores are like all really tightly around kind of like this 80 mark or even a little bit above 80. So this isn't always the case. This is not reflective of what's going to happen in this class or anything like that, but this is just one particular semester. And so that's just kind of interesting to see that probably there's more variation, probably a higher standard deviation in the final than the midterm. Not sure, but just kind of eyeballing it seems like that. And if you guys had to guess, like, what do you think the averages might be? Like, what do you think the average score in the midterm is? Just kind of eyeballing it. Like, where would that, that balance point be if this was on a scale and you wanted to balance the distribution? Yeah, some people are saying like 78, like high 70s maybe. Yeah, that's a good guess. And then how about for the final? Yeah, so it looks similar. Might be a little bit higher maybe because you're seeing some scores here out near 100, which you didn't really have up here. It seems like in the midterm, the highest score was probably like close to 90-ish. Whereas over here, we're seeing scores that are like almost as high as 100. So, but then you also have some scores out here a lot more. So yeah, but those are good guesses. That's, you're building the intuition for that. And so one thing we might want to do is let's actually try to compare like individual scores, like someone's midterm to the final and get a sense of like how good it was, or like, just what's the performance. So one way we can do that is convert things to standard units. And so we're just gonna make a function here. We had this in the last lecture as well, but it just writes out the actual formula for standard units. So basically takes in a value x, and then what it does, well, it takes in an array actually x, which is like all the values in your distribution. And then what it says is take all of that entire array and then subtract the average value of the array. So that moves everything to 0, essentially, when you do that. And then divide by the standard deviation. So if you look at, for example, the final score, let's say the average is like 80. I don't know what it is, but let's say it's 80. If I take all the values in here and then subtract 80, this entire distribution is now going to be centered at 0. And so that's why the average of the standard units is 0. And then we'll also divide by standard deviation to kind of squish things appropriately and scale it all. So if you run this function now, we can now use this function on the midterm scores and the final scores. So up here, what we'll do is we'll convert the midterm scores into standard units. So we'll call this midterm SU for standard units, and then add it to the exams table. So then we'll have exams with column, midterm, and standard units. And then similarly, we'll do the same thing with the final. So convert the final scores into standard units, add it to the exams table. And then now let's look at the first 10 rows of this table. So now we see our original midterm scores, our original final scores. So you could say these units are like points. So these are in points. And then the midterm is now in standard units in this thing. So the units of this are basically like SDs. So it's like how many SDs above the average is this particular individual. And then the final, same thing. So that's also now in standard units. So if you look here, this person here got 91. That corresponds to 1.16 standard deviations above the average for the midterm. And then their final, they got an 88. That corresponds to 0.71 standard deviations above the average. And so it's interesting because 88 isn't that much less than 91. But if you look at these numbers, like that's actually quite a drop. Like 1.16 is quite a bit larger than 0.7. It's almost like 1.5 times 0.7 actually. Whereas 91 is not 1.5 times 88. It's just 3 points more. It's not that much more. So it's kind of interesting. So you can see like things don't totally equate. And then this one's pretty interesting. So this person got an 87 on the midterm. They got an 88 on the final. So they got a higher score on the final. But if you look at the actual relative performance, the 87 was actually 0.8 standard deviations above the average, whereas the 88, which is a higher raw score, is 0.7 standard deviations above the average. So, in terms of how well they did relative to the average, was actually a little bit lower in the final, even though the raw score was higher. And so this allows you to basically compare these two distributions now. And so the important thing to keep in mind here is that the standard units, it's all based on the context of your sample. So if I took this midterm score of 91, right, that 91 is when I convert to standard units of 1.16, this is relative to the performance of everybody in that class. So it's, taking into account the entire distribution, because you computed that average from the entire distribution, you computed that standard deviation from that entire distribution. So this isn't some like universal thing that like 91 is always going to be 1.16 standard units. It's like within the context of the sample that you're looking at. So that's just one thing really important to keep in mind. And so we can also now look at a histogram of the midterm and final, but in standard units now. So rather than the original ones. So now if we look here, the midterm, the 0 is basically going to correspond to the mean. So that's going to be where the average is. So now when we have it in standard units, we can right away really easily see things. So we can right away really easily see that this is where the average was. And then we can also right away see that this 1 corresponds to standard deviation of 1. So this is 1 standard deviation above, this is 1 standard deviation below, this -1. So right away we can interpret this distribution a lot more easily than when we saw it in the original units. Now this distribution looks exactly the same, but the x-axis has changed now. And so now you can actually just see things more clearly. And then similarly with the final score, we can see this is where the average actually is, this bar, and then 1 standard deviation above. So right now with these graphs, it's really easy to tell, for example, that there were some people who got more than 1 standard deviation above the average on the final, whereas on the midterm, not really anybody got more than 1 standard deviation above the average. So you can see that right away very easily. And then similarly on the final, there were some people who got almost as low as 4 standard deviations below the average. That wasn't really the case on the midterm. So kind of more spread out. So before I continue, any questions about standard units and how we calculated that or why we use that? Yeah, so the main reason you use it why is because, again, if we go back up here, right, for example, this person, I think this gives a really good example of why we would use standard units. So this person got a better raw score in the final, but if you want to understand the context of like, is that really a better score, then you want to look at the actual standard units. And so in this case, when you standardize things, it turns out that the score on the midterm, the performance was actually better than the score on the final, at least relative to everybody else in the class. Oh, another good question. Someone said, is the area to the right and the left of the 0 equal? No, it's not. So 0 is the mean, not the median. So the median is the point where everything to the left and the right is equal. In this case, the mean is where it's like the balance point of your histogram. So we have kind of a tail going out to the left here. So the mean is actually going to be a little bit to the left of the median. The median is probably more like maybe 1 bar over or something. So the median is probably over here, whereas the mean is going to be over here. So this, yeah, mean actually has nothing to do with area. It's just how would you balance this histogram? If you have a lot of things sticking out on one side, you're going to have to move the mean out a little bit more to balance it. And then one last question I'll answer is, what's the difference between Z and SD? So SD is kind of giving you a measure of how far away your data is from its average, typically. So that's like one number that encapsulates that. So that's a standard deviation. So like how far are the deviations on average? It's essentially what that's telling you. And then Z is how you convert, is like the value when you convert things into standard units. So if something is in standard units, we usually just write it as Z. So I'll go back to the formula here too. So Z is the standard units version of a value, and then SD is just one component of what's used to calculate Z. Cool. And so, yeah, once again, the most important thing about standard units is it allows us to compare data no matter what the original units are. So, you have a midterm and a final. They're both in points, but like the points mean very different things. The final is weighs more. Maybe it was harder, maybe it was easier. And so comparing things regardless of how those distributions were created, that's really what standard units allows us to do. So let's do a discussion question now that we've spent quite a bit of time on standard units. So we had this table of ages. So we had this one column of ages here, So just ages of people. And then on this other column, we have the same age, but in standard units. So it's not in years anymore, it's in standard units. So we convert things in standard units. And so the question is, looking at just this table, can you try to find which integer numbers are close to, like approximately what is the average age and approximately what is the standard deviation of the ages, just by looking at this table. So see if you can try to figure that out. Okay, cool, you guys are fast. So people are saying the average is 27. So anyone want to give a reason? You can type it out, like why 27 is, why you think 27 is the average? Like what made you realize that? Yeah, so the standard units is close to 0. So we talked about how when you move things to standard units, the average of your data in standard units is 0, which means that the value for age that corresponds to 0 is going to be probably the average. And so, well, it's definitely going to be the average. So in this case, we don't have anything that's exactly 0, but we see these standard units here. This one's like pretty much 0. It's really close to 0, negative 0.03. We see that up here as well. So that's kind of the smallest value that we see in terms of magnitude. And so that's probably the average, is probably around 27. And then how about for the SD? How did you guys know that the SD was 6? Yeah, so someone said if SD is going to be the thing that corresponds to something that's 1 standard deviation above the average. So in this case, the closest number in the standard units column that's close to 1 is this one, 0.99. And so 0.99, that's basically 1. That corresponds to an age of 33. So that means if you're 33 years old, you're 1 standard deviation above the average. And then from part A, we know that the average is approximately 27. So that means 33 minus 27 is 6. So that's approximate guess of the standard deviation is 6. And so that's how you can guess that here. So you can basically understand really quickly what's the average and then what the standard deviation must be. So let's actually look at the data set this came from. So this is actually just the same baby data set that we've been using with like the smoking moms. So let's read in that table, and then I'm going to create ages here, which is just the actual age of the mother, and then we have age in standard units. So just converting the age in years to age in standard units, and it's using the same function that we wrote above. So standard units is a function that we just wrote earlier, and then let's put them both together into a table. And so then we can see them next to each other. So this was essentially the table I just showed you on the slides. So we have age in years here, we have age in standard units here. And then finally, let's look at the average age and the standard deviation of the ages. So again, just by looking at this table, most people were able to guess that the average is probably 27 because standard units is close to 0 for 27. And then the standard deviation is probably 6 because you want to the value that corresponds to 1 in the standard units here is going to be 1 standard deviation above the average. So this value right here is roughly 1. That means that 33 is 1 standard deviation above the average. And so if I can just write this out here, what it basically means is 33 must equal the average plus 1 SD. And so we know that the average is 27 roughly because that's where standard units is 0. So I can write this as 27 plus 1 SD. And so therefore, if I just subtract 27, I get that SD must equal 6. And so let's look at the actual values. And so the actual average is 27.23. The actual standard deviation was 5.81. So pretty close to what you guys guessed. So it's not going to be exact because this standard deviation wasn't exactly 0, but it was like close enough to 0. And so that gave you kind of a way to guess what it is. Cool. So that's standard units. And then what's interesting about standard units and the histogram, there's some relationship there, which is kind of interesting too. And so we saw just now how like when we were looking at a distribution of like the final exam scores, just straight off the bat, it was really hard to really understand like what the standard deviation is. We had kind of a good guess of the mean. A lot of people said like the mean of the final exam was probably around 80. But just by looking at the histogram, it's really hard to tell like what the actual standard deviation was. And that's because the histogram isn't bell-shaped. But what's interesting is if the histogram is bell-shaped, then you actually can tell pretty well just by looking at the histogram what the standard deviation is. It's pretty cool. And we'll go over that right now. So just to show you what I meant by that. So this histogram here, when we looked at it, we had a good sense that the average is probably around 80-ish, but we couldn't really tell like what the standard deviation is just by looking at this. And so this isn't bell-shaped. A bell-shaped curve is like a symmetric curve that like kind of goes down and then starts to flatten out on the edges. So this isn't that type of a curve, because this curve kind of goes up and then goes down to the left. Like there's a left tail to it. So this is not a bell-shaped curve. But if you do have a bell-shaped curve, then you actually can look at it and visually you can see where the standard deviation is, which is really cool. And so this is the way it works. So if you have a bell-shaped curve, so if you have some data that happens to look like pretty much like a bell-shaped curve, then you know the average is going to be the center of that distribution, like smack in the middle, basically the same as the median. It's going to be like right in the middle. And then the SD is actually the distance between the average and the point of inflection on either side. So if you don't know what point of inflection is, don't worry, I'll explain it right now. But this is an interesting property of a bell-shaped curve. So you can find the center very quickly, and you can find what the SD is as well, just by looking at the distribution. And so let's actually see an example of this from something that's like roughly bell-shaped. So I'm going to go back to the births data set here, and then we're going to look at the maternal heights. So this is the heights of the mothers, and then we're going to draw a histogram of that. And so if you look at this histogram here, this seems to be like kind of bell-shaped. It's basically symmetric, and you see this shape where it kind of like, you have this sharp drop, but then it flattens out at the edge. It doesn't just like keep going down, it starts to flatten out at the edges. And so that's essentially a bell-shaped curve. And so that's what we have here. And so it's kind of interesting that, you know, we can tell, for example, that the mean is going to be in the middle. So in this case, like what, you know, the mean is going to be probably around like 64.5-ish, something like that. We can just tell that by looking at this very easily. Now we were able to tell that with the final exam score pretty decently too, but here I think you can make an even better guess because things are symmetric. So you know that like that's going to be the balance point is going to be the middle point because like things look the same on both sides. So that's kind of how we could guess where the mean is. And then the inflection point, that's the point where when you look at the curve and it like starts to go down steeply, but then all of a sudden it like starts to flatten out. That point where it starts to flatten out, that's called the inflection point. So if you look at this, if we just follow my cursor here, right? We have this curve, it's like goes down, it's like getting really, really steep. It's like a cliff, it's like going down, but then now all of a sudden it starts to flatten out. So it doesn't really like go straight down to the ground. It actually like flattens out nicely like this. And so the point where it kind of like makes that transition is like somewhere around here-ish, I would say. It's hard to see and I'm just kind of eyeballing it, but roughly around there is where it's making that transition. And so, you know, I think that's probably around like 66.5-ish, because this is 67.5. So I think 66.5, like somewhere around here is basically where I would say that transition is happening. And again, it's just a guess. This isn't, what I'm saying isn't like totally correct. That's just kind of me eyeballing it. But that's kind of what I think what's happening. And then if we want to actually, so basically I was saying that the mean is probably at 64.5 because that's corresponding to this bar. That seems like roughly halfway. And then it looks like the inflection point is 66.5. So because of that, that means that this distance is supposed to be equal to the standard deviation for a bell curve. So that means the standard deviation is probably 2 because this is 64.5. This is roughly 66.5. So I'm going to claim that standard deviation is 2 based on that. So that's just my guess. And so we can actually take a look at what the actual values are. So looks like the actual average was 64. So I was off a little bit. So it's actually 64, not 64.5. And then the standard deviation is 2.5. So the 2.5, actually, if you add it to 64, you get 66.5, which I was talking about. So I was kind of right about the inflection point. I wasn't totally right about the center. But this is just showing you kind of what's interesting about bell-shaped curves is you can kind of guess the not just the center, but also what the standard deviation must be just by looking at the curve, which is pretty interesting. And then so just to verify, we can look at these two values here. So, oops, let me move this to a different cell. So this is one standard deviation above the average. Or sorry, let me write, this is showing the wrong thing. So this is one standard deviation above the average. So I'm just taking the average, adding one standard deviation, that's 66.5. And then one standard deviation below the average, that's 61.5. So if you go to this graph here, 66.5 we talked about is like somewhere over here, and then 61.5 is probably somewhere over here. And so those seem like the points where like if you were to kind of draw an imaginary line through all the bars, it seems like that's where like it starts to get flattened out. So it's like really, it's getting steeper, 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 like falling faster, but then now it's flattening out and like going out slowly. So that's the inflection point. And then that corresponds to 1 standard deviation away. And so to show that to you a little bit better, let me just add actual graphics on top of it. So this was the same graph we just saw. And then this is kind of 1 standard deviation above. This is what we found was 1 standard deviation above the average. This is what we found was 1 standard deviation below the average. And so what I mean by inflection point is the region in here is like the way this curve is going. It's kind of like, it's like upside down U basically. This is called concave basically. So it looks like an entrance to a cave. Think of it like that. And then this is like a cup. So it's like, it's going upwards. So this is convex, but basically this is like up like a cup. Just think of it like that. And this is like down like a frown or a cave. And so the idea is when you see that change happen in the way that the curve is moving, that's the inflection point essentially. So like over here, it's like going down, it's getting like steeper, 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 but then all of a sudden it starts flattening out. And so that point where it starts flattening out, that's the inflection point. And so basically what we're saying is that a bell-shaped curve has exactly 2 inflection points, one on the right, one on the left. And so both of those inflection points correspond to 1 standard deviation away from the mean. So it's like kind of interesting. And so I wouldn't worry too much about, understanding like what an inflection point is and all that stuff. Like you don't need to really know this term, but the main thing is just, when you're looking at a bell-shaped curve, that point where it looks like it's like starting to flatten out, that's 1 standard deviation away from the mean. That's the main thing to keep in mind. And that's a good way for you to just be able to like guess what the standard deviation is by looking at the histogram. That's the most important thing. Cool. So this bell-shaped curve that we keep seeing, it actually has a name. So it's called the normal distribution. And so it has a name because it has all kinds of really interesting properties in statistics that are just incredibly useful for a variety of things. And there's like different kinds of normal curves with different values and centers. But if you have a normal curve that's centered at 0 and has a standard deviation of 1, that's called a standard normal curve. So it's like essentially like take a normal curve and put it in standard units. So that's called standard normal curve. And it has this formula, and you don't need to worry about this formula at all. And if you take like additional classes in statistics or probability or engineering, like you'll definitely see this formula again. But yeah, you don't need to worry about it. But just showing it to you for fun because it has like all these cool things. It's like E and pi and all this stuff. So it's a great formula, and it's pretty cool. So this is an actual normal distribution. So this is like a perfect normal distribution. What we saw so far with the heights of the mothers, that wasn't a normal distribution, but it was something that looks approximately normal. That's how we would say that. So that's like an actual like empirical distribution that looks like it's normal. This is an actual like theoretical normal distribution. So in reality, when you're collecting data out in the real world, you'll probably never actually encounter this theoretical normal distribution, but very often we'll see data in the real world that looks very similar to this shape. And so again, so if you look here at this curve, right, it kind of starts like this. So I'm just gonna start from the center and go out to the right. So it kind of starts curving down and it looks like it's getting steeper and steeper, but then it starts like flattening out and then it actually starts flattening upwards. So over here, it's like kind of dropping down sharply, but then doesn't actually drop down sharply. It like flattens out and then starts kind of tapering off essentially. So that point where it makes that transition, that's called the inflection point right here. And then it turns out that that inflection point is exactly 1 standard deviation above the mean. And so this is just showing that relationship again. Easier to see it here because this is in standard units. So we know that in standard units, 1 on the x-axis means 1 standard deviation. And -1 means 1 standard deviation below. And oh, someone asked, can we ever truly make accurate inference unless the form is like a true normal distribution? So you can actually make really good inference, even if it's not completely normal. And we'll see some examples of that right now, actually, but and in the next lecture. But there's just a lot of very useful properties about this distribution. And so if you have something that looks pretty close to it, you can make the same kind of assumptions, and then you can have the same results, which are interesting. So let's go through some of the interesting properties of normal distributions. So firstly, we've been asking this question many times, how big are most of the values? And we talked about how with Chebyshev's inequality, if you know the standard deviation of your distribution, you can make some pretty good guesses on like how much data must lie within one standard deviation or within two standard deviations or within three standard deviations. So you can make some certain, that at least a certain amount of data lies within two standard deviations, for example, using Chebyshev's formula that we talked about last time. And so with normal distributions, there's an even more specific thing you can say that's like even stronger. And so again, Chebyshev's inequality says this first statement here. It basically says, no matter what your distribution looks like, you don't need to even like look at your histogram. If you know what the standard deviation and you know what the average is, then you know that certain chunk of the data, at least that much data must lie within the average plus or minus a few standard deviations. And so you can go back to the formula to see what exactly that was, but you can actually calculate that for every like 1 SD, 2 SD, 3 SDs away from the average. And then for a histogram that's bell-shaped, so something that looks like a normal distribution, almost all the data is within 3 standard deviations. So that's what's really special about the normal distribution. Whereas if you go back and look at Chebyshev's formula, 3 standard deviations doesn't really correspond to all of the data, almost all the data. It is a pretty large number, but it's not almost all the data. But with a histogram, you can't say that. So you have a little bit more confidence on how much data is within 3 standard deviations for a histogram. And if we're being like really specific about it, this is actually what the numbers break down to. So if you want to know how much data is within 1 standard deviation of your average, so like 1 standard deviation above or 1 standard deviation below, how much data is within that? If you use Chebyshev's inequality, the answer you would get is at least 0%, which is not very helpful. But if you know that's a normal distribution, then you know that it's about 68% of the data. Roughly, we're saying about not because the number isn't unknown. I'm just like rounding, but it's 68% of the data. And then if you want to see how much data must lie within 2 standard deviations, again, if you don't know anything about the distribution, all you know is the standard deviation and the average, then you can say with confidence that at least 75% of the data must be within 2 standard deviations using Chebyshev's inequality. But then if you also know that not only do I know the average and the standard deviation, I also know that this is a normal distribution. If you know that third fact, then you can be even stronger and say, actually, I know that 95% of the data is within 2 standard deviations. So you have more information, you can make an even better guess. And then the same thing holds when you go to 3 standard deviations. So with Chebyshev, you would say at least 88%, but if you know it's normal, you can say it's at least 99.7, which is like basically everything. And so that's why this is one reason why normal distributions are so powerful. So before I continue, any questions about this, the difference between normal distribution and just like any other distribution? Oh, that's a good question. Does the 2 standard deviations, 95%, have some relationship to 95% confidence intervals? So yes, there is a relationship there. Very, very cool observation you made. So up until now, when we've made confidence intervals, we've done things like bootstrapping, right? So we wanted to understand like what's the distribution of our statistic, and one way we would try to simulate the distribution of the statistic is we would just bootstrap our sample many, many times. And that would allow us to kind of approximate it. And then we would create this like 95% confidence interval. And so we created that interval using the bootstrap, which made no assumptions about what the distribution is. We don't know what the distribution of this statistic is. But what's interesting is if you do know that a distribution of a statistic is normal, then you don't need to do any bootstrapping at all, actually. You can just say, I know that this distribution is normal. I know that it has this standard deviation. Therefore, my confidence interval is literally just 2 standard deviations, and then I'm done. So it's really easy to make confidence intervals when you know that your distribution of your statistic is normally distributed. And in all the past lectures, we didn't assume that. We didn't know that things were normal. So we bootstrap. That's why we had to bootstrap. But yeah, that's a very good question. Oh, the Chebyshev, that was in the last lecture. So check Chebyshev's inequality. We talked about that in the last lecture. So someone said, what kind of distributions? You have right tail, left tail, normal, anything else? So there's all kinds of distributions. You can have distributions that are like U-shaped. So you only have data like on the ends of your range and nothing in the middle. But you can have distributions that look like this. You can have distributions that look like this that have like 3 humps. Like this is all kinds of distributions. Typically in this class, we'll mainly see things that are, I guess, left tail, right tail, and normal, I guess. Yeah, like bell-shaped. Typically, those are the main ones to worry about. Does the plus minus mean above and below, or do you actually add and subtract the SD? Yeah, so you actually literally add and subtract the SD. So this is basically saying, if I look at the average minus 2 SDs and the average plus 2 SDs, we know that in between those 2 points, at least 75% of the data is going to be there for any distribution. And if it's a normal distribution, we know that at least 95% of the data is going to be between those 2 things. So you do have to like literally add that on each side to come up with 2 numbers. This average plus or minus basically means 2 numbers. Find those 2 numbers, and then the stuff that's in between those 2 numbers is equal to one of these percentages, depending on how much information you have about the distribution. And yeah, a lot of people are asking like, what's considered normal? How do you know it's normal? There actually are ways that you can check whether something like looks really normal, and that's kind of beyond the scope of this class. There's actually mathematical ways you can do that. But separate to that, for this class, mainly we'll just be kind of, you'll be told if something is approximately normal, and it's really just more like an eyeball guess. But there are systematic ways to do that, I would say. And so going back to the 95%, this is kind of visually what that means. So basically our average is at 0. And then if you go add 2 standard deviations above, if you add 2 standard deviations below, basically this area in between is 95% of all the data. And so this is going to be true for a theoretical distribution. And then if you have something that's approximately normal, it'll be roughly true. It's not going to be exactly true, but it should be roughly true. I shouldn't say roughly true, that's bad. I should just say it's either true or false. But basically it's like roughly accurate. That 95% of the data is within 2 standard deviations. If something is like approximately normal. Cool, so this is what those bounds are referring to. And then finally we get to the central limit theorem. So this is probably one of the most useful things for the normal distribution. So, being able to say that 95% of the data is between 2 standard deviations, that's great, but this is even more powerful. And this is like probably the most useful thing about normal distributions is the central limit theorem. So I'll try to go over this slowly. So central limit theorems specifically describe something about sample averages. So, we've talked a lot in this class about different things that you could try to estimate. You could try to estimate like the median of some population. You could try to estimate like what's the maximum value of something in a population. This is specifically talking about estimating the average, the mean. So if you're trying to estimate the mean and you're using the sample average, so like basically sum up all the values in your sample, divide by the number of things there are, that's the sample average. So if you're using that specific statistic, there's some really cool properties about that statistic that you can use to your advantage. And so that's related to central limit theorem, basically. It's talking about how you can use that with normal distribution. And again, why do we care about sample averages? Because that's how we estimate population averages. So if you want to know like what proportion of people in a particular state are voting for a particular candidate, you would like to be able to get the entire population of that state, or at least everybody who's an eligible voter, and ask every single one of them who they're going to vote for. But that's really hard to do, very expensive, takes a lot of time. So what do? You take a sample of people and you ask them, and you take the average. So you see like what proportion of people on average in your sample are voting for a particular candidate. And so that's why sample average is very useful. They're used to estimate the average of the entire population. And so, oftentimes when you're estimating things, we've talked about this before, but just getting one number as your estimate typically isn't good enough. You want to also get a sense of how, what's your variability of your estimate? Like how good is your estimate? If you have a sample size of like 10, it's going to vary a lot more than if you have a sample size of like 1,000. And so when you report statistics to people, or like in a study, it's better to give more than just that one estimate that you got. You want to also give some sense of like, okay, this is my guess, but I also think it could be like somewhere in this range. So that's really useful to be able to create that sense of confidence. And so the central limit theorem allows us to create that sense of confidence in a slightly different way that's even like easier. And so it only holds under certain conditions. So specifically, you need your sample size to be really large. And you need to make sure that everybody in your sample is drawn at random with replacement. And what's really powerful about this is if you can satisfy those conditions, then regardless of what the distribution of your population looks like it doesn't matter if your population is like left skewed, right skewed, like U-shaped, doesn't matter how people are distributed in your population. The probability distribution of the sample average, which is like, that's your estimate. So the probability distribution of your estimate, not the values in the population, but of your estimate, that is going to be roughly normal. That's basically a central limit theorem. And so that's what's really powerful here is, again, we've used things like bootstrapping in the past to try to estimate the probability distribution of our statistic. But now you know that if your statistic that you're trying to look at is specifically the sample average, then as long as you satisfy these conditions up above, not only, you don't even have to bootstrap anymore. You could just assume that it's a normal distribution, essentially. And so that's really the big thing here. And it's pretty crazy because like there's this specific distribution and somehow the sample average is like normally distributed. And no other statistic is like this. So it's like a really kind of crazy result, but it's very, very powerful. And so someone asked how large is large. So we'll talk a little bit more about that, I think next week's lecture. So we'll go over some specific things on like how large you need to make things to get a certain level of accuracy. But for this theorem to hold, it's like, it should be pretty large. I mean, there's no actual numbers. So people say like above 30, above 100, typically larger the better, I would say. But yeah. Cool. So now that we know what the central limit theorem is, let's actually take a look at it in action. So let's see if this actually holds. Let's try to look at the sample average of some data set, some sample, and then see if it actually has a normal distribution or not. So for our example, we're going to look at those flights of the delays from the United flights in summer of 2015. So just to recap this again, we have like, if every row is a different flight, I believe these are all leaving out of SFO actually. And then each row we have the date of the flight number, what the destination was, and then the delay in minutes. And so we had these delays, and then if you look at the histogram of the delays, this is a right tail distribution. So most of the delays are around 0, but you do have this kind of tail going out to the right where sometimes you have delays as high as like 50 minutes, 100 minutes. It looks like we even get up to like almost 300 minutes sometimes, although it's so infrequent that you don't even see it on this graph. But we do get really long delays like that here. And so one thing we can do is, this is the population. So we have access to all the flights in the summer. So this is our population that we're trying to study. So I don't need to do any sampling. I already know, I can just look at the mean and standard deviation and I'm done. Let's just do that. So we know the mean delay is 16.65, which is like somewhere out here. And then we know the standard deviation is 39. So that's actually pretty large, 39. And then we can also look at the 50th percentile. So the 50th percentile, which is the median, that's a flight delay of 2. So as expected, this is a right tail. So that's why the mean is bigger than the median. The mean kind of gets pulled out to the right by all these outliers over here. And so it's larger than the median. But if I was trying to understand like the mean flight delay of this population, I already have the population data, so I'm done. I don't need to do anything more. But for the purpose of this, let's assume that we didn't have this population. So let's assume that for some reason I couldn't actually get all of the data from all of the flights in that summer. I could only sample some of them. And I have to guess what this true mean of 16.65 is using some sample that I gathered. And so let's actually try to simulate that process. So we're going to make a function here called one sample mean. And what it's going to do is it's going to take in a sample size. So we can specify how big we want our sample to be. Do I want to sample like 100 flights, 200 flights, whatever it is. And what it's going to do is it's going to take our table, our population, sample from it of sample size. And then once we have our sampled flights, we just calculate the average delay. So that's all this function does. And so this allows us to simulate taking a sample from the population, calculating the sample average, and then seeing what the result is. So we got that. So now let's do it one time with a sample size of 100. So we'll run this. So we ran this once. We happen to get a mean flight delay of 23.54. Right? And so this is our sample average from 100 sampled flights. Now we know that the true flight delay of all of the flights is 16.65. And we're trying to get to that number as best as we can. And so if I run this again, let's take another sample. Now we happen to get an average delay of 20.6 minutes. Can run it again. Now we got something that's pretty close. So by chance, we got something that's actually very close. Run it again. Now it's like even closer. Run it again. Now it went a little bit farther away. So you can see how it kind of jumps around. And so the idea is I want to understand the variability of this estimate, because every time I take 100 flights, I'm going to have a slightly different estimate. And so I want to get a sense of like what's the variability of this estimate. And so typically in the real world, it's really hard to do that because you just get that one sample. But in this case, we have the entire population. So we can just sample from this all day and simulate it multiple times. And so let's make a function here that allows us to do that sampling procedure 10,000 times. So we're going to call this 10,000 sample means. And then we're going to have this parameter sample size, which is what should the sample size be in each of the 10,000 simulations. And so the way we write this function, so we're going to store all those 10,000 simulations in a value called means, and then we'll do for I in input range 10,000. So 10,000 times, what are we going to do in each simulation? Well, firstly, we're going to simulate a single sample of size, whatever our sample size is. In this case, it was 100, so we'll do it with 100 right now. So whatever sample size is, do a sample of that size, calculate the mean of it, and then just store that mean in our array. And so in the end, we should have 10,000 means from 10,000 different samples. So we have our function now, and then let's actually now run this function, assuming a sample size of 100. So this takes a little bit of time, and then what it does is basically 10,000 times, it's going to do a sample of size 100. So sample size 100, calculate the average delay. Sample size 100, calculate the average delay. Do that 10,000 times. All right, so now we have 10,000 average delays, and then we can just look at this. So these are the average delays we got. So, one time we got 17, 17, 10, so on. So you can see how it's jumping around. And just to verify, this is 10,000 values. And so now we can finally draw a histogram of all of these simulated sample delays. And so let's take a look at our histogram. And so this is the histogram that we see. So again, the actual population average that we're trying to estimate is 16.67. And then this histogram is showing what estimates you would get if you took a sample size of 100. So sometimes if you take a sample size of 100, you'll get an estimate as high as 30. Sometimes you'll get an estimate as low as 10, but your estimate's pretty close in general. So it looks like with a sample size of 100, we tend to do a pretty good job. That's basically what this is telling us. And then as we can see, it's not completely bell-shaped. It looks like there's a little bit of a tail to the right, but it's almost getting there. It's almost bell-shaped. So, 100 is a pretty large sample size. And so it seems like that normal distribution assumption is like kind of decent here. Now let's try the same thing, but with 400. So we're going to do 10,000 simulations again, but this time we're going to sample 400 flights in each simulation. So now if we do this, let's see what happens. So this takes a little bit longer because they're doing 400 flights in each simulation. But again, we're going to visualize what the estimate looks like when you have 400 flights in a sample. And we'll get to see like how that varies. So again, this one, just like the other one, it's centered at around the actual value of 16.65, which is around here. But this one looks a lot more bell-shaped. There doesn't seem to be as much of a tail going out to the right or the left. They're kind of pretty much symmetric here. And so this is essentially the central limit theorem in action. So this is basically telling us that if you have a large sample size, the variability of your estimate is roughly normally distributed. And that's kind of what we're seeing here. So you can just kind of compare these two. So this is when we had a smaller sample size. the center was like still pretty close to the actual value, which is good, but it did have a little bit of a right tail. But now once you get to like 400, it's like looking a lot more symmetric now. And then if you did like 1,000, it would look even more like a normal distribution. So that's kind of the differences there. So I think we'll stop there. That is actually the last slide. But if there are any other questions, I'll stay on to answer.